Welcome to Scholars Air Tutorial. In this video, we'll be looking at a topic called sound wave, a very important topic in physics. First of all, let's look at three important concepts of sound wave. So the first one, by definition, sound is a form of energy produced by vibrating bodies. Sound is a form of energy produced by vibrating bodies. Number two concept says, this vibration of sound wave causes a disturbance which travels out from the source of vibration in form of longitudinal waves, meaning sound waves are also longitudinal waves. Longitudinal waves are waves which travels in a direction parallel to the vibration of the medium. And the number three concept says sound wave travels through air, water or solid, meaning that sound waves require material medium for their propagation. Hence, we can say sound waves are mechanical waves. So it is also right to say that in space where there is no air, sound does not exist. So note these three important concepts of sound waves. Now, for sound to travel, meaning they have a velocity. So let's look at velocity of sound waves. Sound travels at a velocity of 340 meter per second. 340 meter per second. So we have V sound equals 340 meter per second. Since sound is a wave, recall that if we have the velocity of a wave as velocity V, frequency F, and we have wavelength lambda, the symbol for wavelength is lambda. These three quantities has a relationship, and the relationship is velocity is the product of F and lambda, of frequency and wavelength. So hence we have V equals F lambda. Now let's look at the units for these quantities. For velocity, velocity is measured in meter per second. For frequency, we have hertz, and for wavelength, we have meters. Now that we've known this, let's look at some questions. Let's see how we can apply the little knowledge in solving problems. Question 1 says, what is the distance between two successive crests of a sound wave vibrating at a frequency of 455 millihertz in air? And we are given velocity of sound in air equals 340 meter per second, which we've already established. So we write out our solution. First of all, before solving any question, the first thing to do is to write out your parameters. So given in our question, they said two successive crests, the distance between two successive crests. Now the distance between two successive crests is called wavelength. So given first we have distance between two successive crests, which is our wavelength. So our wavelength is lambda, and we are asked to find the wavelength. Because they say what is the distance between two successive crests, so we are asked to find the wavelength, and we are given our frequency F as 455 millihertz. 455 millihertz. Since it is a millihertz, we convert to hertz, and converting to hertz, we multiply by 10 raised to the power of minus 3. So we have 455 times 10 raised to the power of minus 3 hertz. And we are given velocity V as 340 meter per second. So recall that V equals F lambda. V equals F times wavelength, that is frequency times wavelength. So we have frequency, we have velocity, and we are asked to find wavelength. We make lambda, which is wavelength, the subject of the formula. For us to make it subject of the formula, we divide both sides by F. And if we divide both sides by F, we have lambda equals V over F. Now let's substitute our values. For V we have 340, and for F we have 455 times 10 raised to the power of minus 3. So we have lambda equals V over F, which is 340 divided by 455 times 10 raised to the power of minus 3. And if you solve correctly, this will give us 747.25. And we said wavelength is measured in meters, so we include our units meters. So the answer to this question is 747.25 meters. Now let's solve another question. One more question before we move ahead. Question 2 says, what is the period of vibration of a sound wave of wavelength 256 cm? What is the period of vibration of a sound wave of wavelength 256 cm? So first of all, we write out our parameters. Given wavelength, which is lambda, as 256 cm. Now it is given in cm. Recall we said the unit is meters, so it was given in centimeters. What do? We convert to meters. Converting centimeter to meter, we divide by 100. So we do 256 divided by 100, and that will give us 2.56. So we have 2.56 meters. So our wavelength is 2.56 meters. And we have period of vibration. We are asked to find the period of vibration. Period of vibration, which is T. So we are asked to find T. Now recall that whenever you are asked to find T equals 1 over F. That is, T is the inverse of frequency. The inverse of frequency. So T equals 1 over F. So since T equals 1 over F, in this question we are not given frequency. So we have to first of all find F. Now recall that V is equals to F lambda. And we were given lambda in this question as 2.56 meters, but we are not given V. Recall that V is a constant and V equals 340 meters per second. Remember we said sound travels at the velocity of 340 meters per second. So we have our V, which is a constant, as 340 meters per second. So with this we can solve for F. Inputting our values, we have 340 equals F times 2.56. In order to make F the summation of the formula, we divide both sides by 2.56. And we have F equals 340 divided by 2.56, which will give us 132 or 132.81 hertz. Remember, this is frequency, so it's measured in hertz. Now recall we said earlier that T is the inverse of frequency. That is to say that T equals 1 over F, and we have our F as 132.81 hertz. So to get C, we do 1 divided by 132.81, which will give us 0.0075 seconds. Period is measured in seconds. So this is the answer to this question. Moving ahead, let's look at properties of sound wave. For this video, we'll be looking at only one property. Recall we have properties of wave like reflection, refraction, interference, diffraction. So we will be applying these properties of wave into sound wave. So the property of sound wave we'll be looking at is reflection of sound wave. First of all, what is reflection of sound wave? Reflection is the change in direction of a wavefront at an interface between two different medium, so that the wavefront returns to the medium from which it originated. That is to say that reflection of sound gives rise to the concept of echoes. You can see from the definition, it says it is the change in the direction of a wavefront at an interface between two different medium, so that the wavefront returns to the medium from which it originated. So this is just the concept of echoes. What then is an echo? When we say echo, the echo I'm talking about is the one you are familiar with. An echo is a sound heard after the reflection of sound waves from a plane surface. An echo is a sound heard after the reflection of sound waves from a plane surface. So echo are produced by sound wave when they are reflected. Now let's look at some key concepts of echoes. Firstly, echoes are affected by distance and can only be heard when the minimum distance between the source of sound and reflecting surface is about 17 meters. That is the first concept. Don't worry, I will show you how we arrived at this 17 meters. Understand this one. Echoes are affected by distance and can only be heard when the minimum distance between the source of sound and reflecting surface is about 17 meters. And number 2 says echo can also be heard separately from the original sound if it arrives at least 0.1 seconds later. Echo can only be heard separately from the original sound if it arrives at least 0.1 seconds later. This concept is, as I'm talking, for every sound made there is an echo, but can you hear the echo of that sound? Can the echo be heard separately from the original sound? So this second concept is telling us that echoes can only be heard separately from the original sound if it arrives at least 0.1 seconds later. Now recall that velocity, which is v, equals distance over time. That is to say that velocity equals d over t. Applying this to echo, if we have a boy here, this boy we call it the source, and we have a wall, a boy and a wall, they are at a distance. The boy makes a sound. Now this sound this boy makes travels to hit the wall. It travels towards the wall, because if you make a sound, it will travel towards the wall, and then because it is a wall, it will bounce back, which is what we call reflection of sound wave. It will bounce back to the boy, which is these two arrows you can see here. You can see the first arrow, which is the sound wave moving towards the wall because the boy is making a sound, and then it hits the wall, it tends to bounce back. So this sound that is bouncing back is what we refer to as echo. That is why we said echoes are produced by sound wave when they are reflected. So this sound hits the wall and it is being reflected back to the boy. Now you can see that there is a distance between this boy and the wall. That distance, we have the first distance, which is distance for the sound to travel, the sound wave to travel from where the boy is to the wall, and the distance for the sound to be reflected back to the wall. So this distance, we call it the total distance of sound wave, or you can call it capital D. Instead of small d now, we call it capital D. And if we further break down this capital D, we know that capital D is gotten from what? 2 times D. 2D. 2 times D is what? 2D. Because the distance for the sound to travel to the wall and the distance for the sound to travel back to the, or to be reflected back to the boy. So there are 2Ds. So capital D equals 2D. So 2D is the total distance of the sound wave. Now from V equals D over T, if we make T the subject of the formula, you would have T equals D over V. And we said that D equals 2d in echo. This applies in echo only. D, capital D, which is the total distance of sound wave, equals 2d. Therefore, t, which is our time, equals 2d over v. So the capital D is the total distance of sound wave, and the v is the velocity of sound in air, which if we simplify it, we say t equals 2d over v. The 2d is the total distance of sound. The 2d is the total distance of sound wave, which is the illustration I just gave now. Now recall the second concept of echo, which says that echoes can also be heard separately from the original sound if it arrives at least 0.1 seconds later. That is to say that the time for echo to be heard separately should not be less than 0.1. So if we are expressing this mathematically, we are saying that the time should be greater than or equal to 0.1 seconds. The time for echo to be heard separately should be greater than or equal to 0.1 seconds. Now recall that we just said t equals 2d over v, and we know that v is equal to 340 meters per second, which is what we established earlier when we said sound travels at a velocity of 340 meters per second. So since v equals 340, we substitute it and we'll be having t equals 2d over 340. No longer 2d over v, but 2d over 340. So since we know that the value for t is 2d over 340, we bring it back to this relationship we just expressed now, which is t should be greater than or equal to 0.1 seconds. So 2d over 340 should be greater than or equal to 0.1. And we solve this how we solve questions normally. We cross multiply. So for us to have 2d, for us to have the value of d, we cross multiply. So 2d will be greater than or equal to 0.1 times 340. 0.1 times 340 is 34. So we have 2d is greater than or equal to 34. In order to have d, we divide both sides by 2. And if we divide by 2, 34 divided by 2 is 17. So our d should be greater than or is greater than or equal to 17 meters. Now this d means distance. So distance is greater than or equal to 17 meters. So you can see that the distance before you can hear an echo should be greater than or equal to 17 meters. And this is how we got our first concept, our first key concept, where we said echoes are affected by distance and can only be heard when the minimum distance between the source of sound and reflecting surface is about 17 meters. It said the minimum distance should be what? 17 meters. So this is how we arrived at this 17 meters. Meaning that the distance should not be less than 17 for an echo to be heard separately. So it should be greater than or equal to 17 meters. So we can say the distance between the source of the sound wave and the reflecting surface. The illustration we gave between the boy and the wall, that boy is called the source of the sound wave because it's the one making the sound. The reflecting surface is the wall. So the distance between the source of the sound wave and the reflecting surface should be at least 17 meters before an echo can be heard. And this is what we meant by the first key concept. Now let's see how we can apply all of this in solving questions. So we'll be solving just 2 questions and we move ahead. So our first question says, a boy standing some distance from the foot of a tall cliff claps his hands and hears the echo 0.5 seconds later. If the speed of the sound in air is 340 meters per second, how far is he from the cliff? So first of all, we write out our given parameters. Given the time as 0.5 seconds later, because it says, and here's the echo 0.5 seconds later. So we have time as 0.5 seconds later. If the speed of the sound in air is 340 meters per second, so our velocity is 340 meters per second. Say, how far is he from the cliff? We are asked to find what? The distance. How far is he from the cliff? Which is distance. Now, recall the relationship we established earlier. We said V equals D over T. That is capital D. Now, for echo, capital D equals 2D, which is 2 small d. So if we replace this 2d, if we replace this d by 2d, we'll be having V equals 2d over T. And in order to make d the subject of the formula, we cross multiply. So 2d is equal to what? Vt, because V times T when we cross multiply. So 2d will be equal to Vt. And we divide both sides by 2. If we divide both sides by 2, we have d equals Vt over 2. So now that we've gotten the formula to solve, we input our values. We have our V as 340 meters per second and time as 0.5 seconds. So d equals Vt over 2. Solving, we have 340 times 0.5 divided by 2. 340 times 0.5 is 170. So 170 divided by 2 will give us 85 meters. And this is our final answer. So the boy is 85 meters away from the cliff. That's the distance between the boy and the cliff. Let's look at the second question. Question 2 says, a sound wave emitted from the bottom of a ship travels at 1,500 meters per second vertically downward through water to an ocean bed 260 meters deep and is reflected upwards. What is the time interval between the instant the sound is emitted and the instant the echo is received? So, solution. First of all, we write out our given parameters. We are given velocity as 1,500 meters per second. You see, the ship travels at 1,500 meters per second. Meter per second there should tell you that it is velocity. So we are given velocity as 1,500 meters per second. We are given distance, which is small d, as 260 meters. You can see through water to an ocean bed 260 meters deep. So small d, we are given d as 260 meters, and we are asked to find time. You say, what is the time interval? So we have to find time. Now recall that V equals capital D over T, and for echo, capital D equals 2D. For us to get capital D, or capital D is equal to 2D, and since we are given our small d as 260, so D equals 2 times 260. 2 times 260 is what? 520. So we have our capital D as 520 meters. Then we bring it back to our initial formula, which is V equals capital D over T, and we are given a V as 15. We have D as 520. So 1,005 equals 520 over T. What do we do here? We cross multiply. If we cross multiply, we have 1,500 T equals 520. And for us to make T the subject of the formula, or for us to find T, we divide both sides by 1/5. If we divide both sides by 1/5, we are having T equals 520 over 1/5. And 520 divided by 1/5 will give us 0.35 seconds. Seconds because that is time. We are looking for time. So the between the instant the sound is omitted and the instant the echo is received is 0.35 seconds. So like I said, we are only going to solve 2 questions. So let's look at something else, application of echoes. First, echo is applied in the determination of the speed of sound in air. The determination of the speed of sound in air. And for number 2, you see echo sounding. Echo sounding. The concept of echo sounding is used to determine the depth of a seabed from a ship, like the question 2 we just solved. Then for number 3, we say exploration for gas and oil. And lastly, detection of submarine. Echo is used to detect the presence of submarine. So don't just be limited to these 4 applications given. You can make more research to know further real-life application of echoes. So the last thing we'll be looking at in this video is the concept called reverberation. Reverberation. Reverberation is an effect of echoes, or should I say a negative effect of echo. A negative effect of echo. Now we have 3 concepts that we'll be looking at that helps us understand what reverberation is and how it can be avoided. So the first one says, in concert halls and auditoriums, multiple echoes can sometimes be a nuisance, brought about by reflection from the walls, floors, and ceilings of the hall. The echoes, together with the original sound, gives rise to long-drawn sound, which confuses the listeners. This continuous occurrence of echoes due to multiple reflection of the original sound is called reverberation. So sometimes in some concerts, you see that maybe when an artist is performing, as he's performing, the audience is also trying to follow him or to sing along. So these multiple echoes causes what we call reverberation, and sometimes it tends to sound like a nuisance or what we call noise. So the second concept says reverberation is the persistence of sound. Is the persistence of a sound after some. The second concept says reverberation is the persistence of a sound after the source ceases. So the persistence of a sound after the source of the sound has stopped, like the person producing the sound or where the source at which the sound is coming from has actually stopped, and the sound is still persisting. It seems like you are still hearing the sound. That is what we refer to as reverberation. So the persistence of a sound after the source ceases is called reverberation. A place where reverberation occurs is said to have poor acoustic properties, meaning the place do not have enough properties that can absorb sound waves. And the third concept is reverberation is reduced in halls by covering the ceiling and walls with soft perforated boards, which can minimize the reflection of sound waves by absorbing them quickly, or by hanging curtains around the hall and having more than one opening in the hall, or having more opening in the wall. So this is the concept of reverberation, and this is where you will be ending this video. But before we end, let me give you guys one to do. Attempt this question. A sound wave emitted from the bottom of a ship travels at 1480 meters per second vertically downward through water to an ocean bed 55,600 cm deep and is reflected upwards, what is the time interval between the instant the sound is emitted and the instant the echo is received? So attempt this question and drop your answer in the comment section. However, if you enjoyed this video, ensure you like, subscribe and comment. Your comment should be the answer to this last question. So like, subscribe, comment and share to your friends too, so they can enjoy from the video lesson. See you in our next video.